Welcome everyone. Good morning. Welcome to our first talk, Bloomberg's first talk. It's Keep Calm and Flink On. Today we'll be sharing our journey disaster-proofing Apache Flink on our data streaming infrastructure at Bloomberg. I'm Niharika. I'm a software engineer at Bloomberg. I'm here with my colleague Mihash, who's also a software engineer and a tech lead at Bloomberg. In today's session, we'll quickly go over what Apache Flink is and how it's being used at Bloomberg. We'll talk about Flink's checkpointing and Job Manager HA and how these features bring reliability out of the box. We'll also highlight some pain points we observed while running Apache Flink on multiple Kubernetes clusters in our infrastructure. With that, we'll introduce Karmada. We'll walk you through our journey integrating Karmada into our infrastructure to achieve application level and cluster level failover. With that, we will conclude sharing some useful key results, some lessons learned, and the future work that is scheduled for this project. So, as we all know, Apache Flink is built with high performance and fault tolerance in mind. This makes it a great framework for business critical low latency application. And those are kind of the applications we see at Bloomberg. Today at Bloomberg, we have around thousands of unique Flink jobs hosted on our infrastructure. They power unique use cases that are critical for Bloomberg's core financial products. Like some of them provide real-time market data insights for traders, analysts, and other financial professionals across the globe. So since these are real-time applications, resiliency is everything on our infrastructure. We want applications to keep running. We want state to be preserved properly. And if there is any recovery, we want them to be quick and correct. In order to build such an infrastructure, the first thing we did was we adopted Flink's official Kubernetes operator. This operator works well with our infrastructure because it is built for Kubernetes clusters. It's built and maintained by the Apache Flink community. And also, in short, it helps managing Flink jobs well on Kubernetes cluster because it treats Flink jobs as a first-class citizen in a Kubernetes native way. And our infrastructure basically is a lot of Kubernetes clusters spanning across several tiers. But lifecycle management is only the first part of the story. In order to run Apache Flink reliably in production, we need fault tolerance. So let's quickly go over Flink's inbuilt fault tolerance mechanisms. The first one is checkpointing, obviously, because checkpoints are like distributed snapshots that capture the operator state and the input offset of the data stream. The way it works is the job manager injects checkpoint barriers into the input data stream at regular intervals. These barriers traverse across all the operators, asking each operator to register its state at that point of time. Simultaneously, the source connector also records its input offset. All of this data is asynchronously returned to an external storage like S3 buckets or HDFS. When a pod or a node hosting a task manager crashes, Flink quickly can recover using the last successful checkpoint stored in this external storage. This works well for task failures, but when a job manager crashes, we want a similar kind of recovery. And to do that, folks can enable Job Manager HA. This can be done using Kubernetes or Apache Zookeeper. At a high level, the concept is that there are multiple job managers running at a given point of time. Only one of them acts as a leader job, and the remaining standby jobs are continuously tracking the state. The leader job is only in charge of coordinating the application, so that once the leader job crashes, a standby can quickly take over and start coordinating the applications. So this is how Flink internally reduces the recovery time. The main limitation over here is that this is great for in-cluster failure. That is when a pod or a node crashes, but checkpointing and job manager really doesn't help for a full cluster outage. Full cluster outages are real. They can happen due to various reasons, like infrastructure blip or manual errors. For example, someone applied a misconfigured kubectl command, wiping out an entire namespace. They can also occur due to control plane issues in Kubernetes, where the API crashed or a certificate expired, leaving the entire cluster unmanageable. So we want to design our infrastructure for this kind of failures as well. Till now, we have seen some approaches adopted by our infrastructure tenants. The first one is what we call the active-passive setup. This is also the most common one. So the idea here is when the active cluster goes down, the last successful checkpoint is used to start the Flink application in a standby or a healthy cluster, and it is recovered using the last successful checkpoint, so there is no loss in progress. This is great, but also this is great for stateful application because it honors the exactly once delivery guarantees, and it ensures that there's absolutely no data loss during the recovery time. But the limitation here is it was manual, and since it's manual, it is slow and error-prone sometimes. For applications with stricter SLAs, we saw an active-active setup adopted by our tenants. Here, the idea is that there are two identical Flink jobs running independently on two different data centers. And they are ingesting data from the same data source. A coordinating service like Apache Zookeeper is used to elect one job as the leader. Only the output of the leader job is passed downstream. The other output is discarded completely. This is great to reduce the downtime because when the active Flink job crashes, the leadership just switches over to the standby Flink job. But if care is not, so the first thing during the failover, we might lose the exactly once delivery guarantees and reprocess the data. So that would be at least once data processing. The second thing is that if we are not careful enough during the failover, there can be data loss. And also one more thing to highlight over here, since there are two independent jobs right now running in different clusters, the state can diverge in between them. So if you fail over after the state diverges, then the failover is a little inconsistent. We saw another version of the active-active setup where the output is passed through a caching layer. The idea is if identical data is emitted, only one of them is promoted downstream. This, again, is good because it reduces the downtime to almost zero because both the applications are running independently. But it comes with a huge trade-off where you need to make sure that the syncs are idempotent or else inconsistencies can flow through. And since you added a caching layer, this architecture also became very brittle. So having said that, as our infrastructure grew, we saw some challenges. We observed some challenges running Apache Flink on our infrastructure. The first one is that each control plane is tied to a single Kubernetes cluster. And like I mentioned before, we have multiple Kubernetes clusters spanning across several tiers. So this means that the infrastructure tenant needs to be cognizant about which application is getting deployed to which cluster. Not only that, they need to make sure that the cluster they want to deploy to has enough resources to host that application. This adds burden to the tenant. And then one more limitation, we observed that in order to set up a proper CI/CD pipeline, tenants need to manage multiple kubeconfig files. From coming to the cluster failover scenarios, like I mentioned, the active-passive setup is slow and error-prone, and the active setup becomes extremely complex and need to be really taken into consideration when adopted. From the infrastructure side of things, for even a minor cluster maintenance became extremely expensive because of the amount of coordination and communication that was required between the platform owner and the platform tenants. Mihash?
Cool. Thank you. So what now? Sorry, can you hear me? Great. So we're a platform that manages a lot of different use cases. And given these challenges, particularly with cluster failover, it started to become more and more of a problem, particularly with users who had a lot of different jobs. Like imagine a cluster going down and then having to manually fail over those hundreds of jobs. Like it does not become sustainable. And so we started to think about how we could create an ideal control plane that could take care of all these issues. So we wanted, ideally, a unified control plane that would not require users to have to manage multiple kube configs. So instead, they could just deploy, manage, and view their jobs from a single place with authentication already handled as well. Additionally, what we really wanted was for this control plane to handle intelligent scheduling as well, keeping in mind resources on the member clusters to which those applications are scheduled to. You don't want to schedule a job to a cluster that doesn't have enough resources to run it. And then lastly, we also wanted it to monitor the health of both the resources, but also the clusters themselves. And in cases in which the cluster might be unhealthy, we want some mechanism to be able to fail over those applications to a more healthier cluster. So at Bloomberg, we really believe in open source technology. And as we started to think about this ideal control plane, we took a look at what was around in the ecosystem and if there were any projects that kind of solve these issues for us. And that's kind of how we were introduced to the Karmada project. So for those who are unaware, Karmada is an open source Kubernetes management system, and it's built to manage cloud native applications across many Kubernetes clusters. And it comes with a wide variety of features. For us platform owners, it enables us to manage a lot of Kubernetes clusters without having to get tenants involved. We can add clusters, we can take them away, and that's all abstracted away. Additionally, it allows us to define how applications are actually scheduled to those member clusters, and we can define fine-grained scheduling properties. For the user, it comes with additional benefits, such as the unified endpoint for viewing their resources, as well as authentication. And finally, it provides support for automated cross-cluster failover, which is what we were particularly interested in. So before we dive into the failover component, I thought it was helpful to kind of go over how Karmada monitors health on both a cluster and application level. They're both similar processes. For cluster health, this is done by just pinging the health endpoint of each API server on the member cluster. This is using the health Z endpoint. So if it returns a 200 response, you're good to go. It states that the cluster itself is healthy. If it returns anything other than a 200 response, or if it's not able to make contact with the cluster at all, it'll mark it as so, and after a certain degree of time, it'll start to flush applications out of that cluster. For the application health, it's a bit more granular. Karmada provides an extensible custom resource interpreter framework, and with that, you can define your own health interpretation schemes depending on the status of the specific resource. So phase 0 for integrating with Karmada was pretty simple. What we use is a propagation policy. So this is a Karmada-specific CRD, which is pretty much just a manifest that tells Karmada what resource are we scheduling and how are we scheduling it. So in this one that we've included in the slide, for example, we wanted to make sure that Flink deployments are just scheduled to a single cluster. So we defined spread constraints that set the min and max groups of which these deployments should be scheduled to make sure that it's scheduled just to a single cluster. Additionally, once it's scheduled, the Flink operator picks up the Flink deployment, it starts running the job, and then Karmada is able to read that status. But one of the limitations in the beginning was that it wasn't able to understand what a Flink deployment status actually is and how to interpret it.
So with that, we hit our first limitation. We needed Karmada to interpret the health of the Flink job in order to successfully fail it over. And for that, we need to understand the failover solution. We had to understand we first need to understand how to measure the state in the Flink before we can define a proper health interpreter for Karmada. So this is how we interpret this. The running state and all the terminal states of the Flink job are considered, we want Karmada to treat these states as healthy. Coming to the ephemeral states, if the application is stuck in one of these ephemeral states, we want Karmada to first look at the error message before interpreting whether the application is healthy or not. We want to do this because, for example, if there is a bad upgrade for a Flink application, the application is bound to be stuck in reconciling mode, and just failing it over to a new cluster will not help it. So we want Karmada to treat that state as healthy, but if the application started but couldn't find enough resources to start up its task managers, that's when we want Karmada to understand that failing it over is a good thing. So that is something we wanted Karmada to interpret properly. And finally, the intermediate short-term states, they transition into a terminal state quite quickly. So we want Karmada to interpret them as healthy as well. So given this interpretation, this is how our failover looked like. So since the application is in running state, we want Karmada is treating that as a healthy state. And once the application moves to a reconciling state based on the error message in the Flink deployment status, Karmada will either treat it as healthy or unhealthy. And if it treats it as unhealthy, based on the decision conditions and the propagation policy defined for that cluster, it will wait for the toleration seconds and purge it and start the application in a new cluster. And then it looks at the status of the application in the new cluster and then treats it as healthy. At a high level, this looked fine, but there is a small problem in this. Can anyone guess what it is? It is that the application started as new. And doing so, the application lost its initial progress that it had done in the previous cluster. So this is our second limitation. We want Karmada to preserve the state so that it knows exactly how to start the application without losing any progress. And for that, we worked closely with the Karmada community and introduced these two fields in the propagation policy. The first one is the JSON path, which contains the actual information that we want Karmada to pass to the new Flink job. And then the alias label, which holds the label key that gets ingested into the resource. In our example, we are storing the job ID, and then the failover job ID is the key of the label that gets ingested. So given this information, this is how our failover look like. Once the application is treated as unhealthy, it will be scheduled to a new application. We use Kyverno to query the database using the job ID to get the exact location of the last successful checkpoint. And that information is injected into the Flink deployment with the initial save point path field. And this information, this CRT is now, this manifest file is now given to the Kubernetes operator, and the operator now knows how to start the application successfully from the last successful checkpoint. And this is how we preserve the state. Yeah.
Cool. So now just to summarize, what were some of the limitations that we ran into when trying to run this in production? So one thing to keep in mind is application failover itself should ultimately be a last resort. Primarily, what we want to depend on is the built-in high availability mechanisms that are provided by Apache Flink. Normally, again, these are long-running jobs. Nodes may go down, jobs might get rescheduled, but ultimately they should be able to recover within the cluster. You just have to give it some time. So really, it should only be in cases where there's a huge problem with the cluster, and then actually have them fail over. However, this has really improved our lives, specifically for users who might have more relaxed SLAs, thinking on the order of like minutes to hours. In those cases, it really helps us by preventing manual intervention outside business hours. But again, this comes with some key limitations. For users who have really low downtime or very high downtime SLAs, where they can't really tolerate more than a couple seconds of downtime, this is just not going to be really acceptable. And additionally, with application failover, the toleration seconds will start counting down as soon as the application is scheduled to the cluster. So you can't set it to be lower than the time that it takes for the pipeline to come up to running. Otherwise, your pipeline is just going to constantly get scheduled across clusters, and that's not going to help. So that's something we're also working with the community to improve. Additionally, the Flink status can be a bit limited. I mean, it does give a good approximation of the pipeline, and the error fields are pretty good. It'll bubble up most of the deployment level errors, but there could be edge cases where a pipeline stops processing and the error isn't bubbled up to the status. In those cases, an application might fail over, and it won't recover because it's depending on another service that might be down or something. So the real solution here is coming down to focusing on cluster health monitoring and failover. So as part of one of the more recent releases, 1.14, we added something called a cluster taint policy. This allows us as admins to define rules for applying and removing taints and conditions to clusters based on specific fields. This is particularly useful for implementing more advanced failover strategies, especially when users have different SLAs. And when combined with taint toleration, it gives us more fine-grained control over failover. So in Karmada, how this works is you have a cluster controller, which is monitoring every cluster. It's constantly pinging the health endpoint of each cluster and appending a condition. In this case, it says that the kube components are healthy, for example. You can also define your own custom controller and add whatever conditions you want, depending on whatever other health attributes you want to monitor. But then in conjunction with a cluster taint policy, that cluster taint policy controller will be monitoring for those conditions. And if that taint exists, or if the condition exists, it'll append a taint to that cluster. So once the taint is actually applied to the cluster, each user can then handle how they want to respond to it. So let's say we've added a no execute taint on a specific cluster. In that case, if you want to be super sensitive to cluster outages, then you can decide to fail over faster rather than other users. But we don't want to set just a fixed failover window because really it depends on what the user needs, and we want to make that configurable for the user. Cool. So let's wrap this up. I wanted to quickly go over, I know we've mostly been talking about cluster failover, but I think one of the biggest benefits of us using Karmada was just the fact that it provides a unified endpoint. And so it simplifies job management for a lot of our users. Again, you could think back to some of the cases we were talking about where users can have hundreds of jobs and they're deployed across many different tiers. Like that really starts to become cumbersome. So by having this unified control plane for resource management, you no longer have to think about all those different kube configs. Comes with centralized authentication as well. And then you also don't have to think about which cluster has which resources. That's all kind of handled by the platform itself. Now, additionally, when it comes to cluster failover, it really did help us improve our system resiliency. We're able to cover cases in which Apache Flink wouldn't be able to recover by itself. So for instance, with high availability mechanisms, let's say you have a cluster and half the nodes go down, but all the other nodes are fully saturated. Even if Apache Flink is trying to restart your job, at that point, that's a problem that's on the kube level. So your job is never going to get scheduled, and there's really nothing you can do besides manually intervening in those cases. So that's where Karmada really comes in handy. Additionally, it's flexible and configurable, so different users have different SLA requirements. If you're more sensitive to failover, you can set your toleration to be a lot lower. If you're a user who doesn't really care too much about how fast it takes, you can decide to have a more conservative toleration. And then lastly, it really has reduced some of the operational burden for us as platform owners. We try to stay up to date with the most recent versions of Kubernetes or the latest OS. And in those cases, I mean, if you're trying to make an upgrade to Kubernetes, because it's so closely linked with the Flink operator, you could have cases where jobs are flushed out of nodes during that upgrade process, and then you have pipelines that restart. And in production, this can be a pretty big problem. So whenever you're updating Kubernetes, you don't really want to have jobs actively running on that cluster to begin with. And then finally, I just wanted to leave with some of the pending improvements that we have on the Karmada roadmap. So we're working on workload anti-affinity support. This is specific to cases in which users have very low tolerances for downtime. So it would be analogous to the case in which Niha was talking about, where we have active-active setups, where we have two duplicate pipelines that are running in tandem, so that if one goes down, Karmada can fail over that application to another cluster. Meanwhile, you have your other application that's still running just fine. That way, you never have downtime. But the thing to keep in mind there is that Karmada won't know that those two applications can't be scheduled to the same cluster. So we need to make sure that there's some sort of workload anti-affinity where you can have applications that never get scheduled to the same cluster, which would violate some of those high availability guarantees. And thank you so much for coming to our talk. Please come up if you want to contribute to Karmada. Then yes, if you have any questions.
Really nice talk. I do have I would say two questions. The first one is that you said about having the centralized control plane. Aren't you creating a single point of failure on the control plane? That is one. And the second one is how do you play with a data residency once you're playing with multiple clusters?
Okay, for the first one, yes, that would be a single point of failure. The Karmada control plane itself is replicated, so we're using two different Karmada control planes that are running in different data centers, and then you have a load balancer in front of it that's sending requests to one or the other, but they're ultimately pointing to one active instance. And then you have a stretched etcd that's shared amongst the two instances, so if one goes down, you're not going to get data loss. The second, with data residencies, do you
so basically with data resiliency, like Mihash mentioned, that the same application can no longer be deployed in two different clusters using Karmada. How we want to do it is using data affinity. And when there is a failover, Karmada definitely preserves the job ID. And using the job ID, it always fetches the last successful checkpoint and starts with that state. So that's how it makes sure that we still have the exactly once delivery guarantees, and when the job starts, there's no data loss, and data resiliency is basically saved in that way. Thank you.
Any other questions?
Slightly off topic, but were you able to integrate Jenkins to automate Karmada?
So actually, we have a lot of users who rely on Jenkins to at least manage their jobs. As long as you have a kube config that's pointing to the Karmada control plane, you can most certainly set up a Jenkins pipeline that is applying those jobs or creating upgrades. That shouldn't change ultimately, because a lot of the existing CI/CD pipelines that our users have created are with regards to Kubernetes, and Karmada is almost like a mirror of Kubernetes. So the kube config concept is the same. It almost fits in without any other changes necessary.
Okay, thank you.
And also it makes the CI/CD pipeline cleaner, because now you're not juggling multiple kube config files. You just have one single one, and everything else is taken care of.
Okay, I think we're one more question, and then I recommend grabbing the Bloomberg team during the break for any additional questions.
Also, thank you for the talk. When you presented the active-active setup, you said you could deduplicate using Redis.
Yeah.
But isn't Redis also creating a single point of failure and or inconsistencies when you have a read replica or whatever?
Yes, yes. So by introducing any type of caching layer, you're introducing that kind of single point of failure into your data pipeline. So unless your application is in dire need of that kind of SLA where no downtime is required, you need to consider that, and also you need to architect your application carefully around that thing so that it doesn't takes down your application.
And have you tried using a distributed consistent key value store? I mean, etcd would be one example.
We don't have.
We haven't. I don't think we have like a use case for users relying specifically on etcd yet, but that's an idea for sure.
I mean, just saying you could use that to consistently across multiple instances get like what has been issued and what not, and depending on that, filter it out.
So right now, with our multiple Kubernetes clusters, we don't have a stretched etcd, I guess.
I think he's talking specifically about like
Deduplication.
Oh, okay. Yeah, I don't think we tried it.
Okay, thank you.
Yeah.
Okay, thank you very much, team.
Thank you.
Thanks again.